Welcome to the TUT seminar. It's my pleasure to introduce our visitor. So this is Francisco Aragón Artacho, if I pronounced that okay?
Yeah.
Yeah, good enough. And the title of his talk is over here. So Francisco has visited already, it was a couple of years ago?
3 years.
3 years ago, okay. Time flies. And he's going to be here for approximately 3 weeks, I think. And are you going to be speaking about the pictures? So I won't ruin anything?
No, you can go ahead.
So there's some connections with Waterloo in our department. So John Borwine is over here. He was here for a couple of years, many years ago. Heinz was a student of John who was here as well. And let's see. And I guess David was here for a 6-month visit. David is a student of France. And I have a connection as well. We both were postdocs with John Borwine. I was many, many years ago. So, Fran, the floor is all yours.
Thank you. Thank you, Henry and Wala, for the invitation. It's a pleasure to be here. It's very nice, especially to be here in summer when in Spain they're having a heat wave and it's horrible. So it's really nice. So, yeah, this talk is based on this work with all these people, but basically what I'm going to talk about is based on my recent work with my 2 PhD students. So they are the ones who deserve the credit, Ruben Campoy and David Torregrosa, and the current one is Cesar Lopez. And of course, I want to dedicate this talk to John Borwine because otherwise I think I wouldn't be here because he was the person who introduced me to splitting algorithms and many things in mathematics, and I learned a lot of him and I will always be grateful. So this is the outline of my talk. It will have basically 2 parts, and if I have time, I will speak a little bit about this 3rd part. And here you have, this is the faces I'm expecting to see from you. So the first part, I think, is very easy to follow, so everyone in the room should be comfortable with that. If not, it will be my fault. The second part, you will start happy, but then your face will start looking like this. So if you want to check your email, you can wait for that part because you will get lost. So I understand that. And if I have time, hopefully I can talk to you about these non-convex settings, which contains some open problems, which I find a little bit annoying because I would like to find the explanation. So let's begin about splitting methodology and what I mean by splitting algorithm. So a splitting algorithm is a numerical method which takes advantage of the structure of a given problem. And the idea of splitting algorithms is to use the divide and conquer paradigm. So for example, I think this is the easiest thing. Imagine that you have 2 sets and you want to find a point in the intersection of these 2 sets. But the only thing that you can do is to use these sets separately. So how can you do that? So I will start with the easiest one. So let me recall projection algorithms. And to do that, let me recall you what is the projection. All the time during my talk, I will be talking about Hilbert spaces. If you don't feel comfortable with Hilbert spaces, don't be afraid. You can think all the time about Rn, Euclidean space, but take in mind that everything works in Hilbert, which means that you can take infinite dimensionals and everything will work. It will make things more complicated, a little bit more interesting, because you can have weak or strong convergence, but you will see. So if you have a closed and convex set like this, the projection, this is the operator that we will use, and you know, it gives you the nearest point to the point x into the set C, so it will be this point here. So the simplest algorithm and one of the simplest feasibility problems you can think of is to find a point in the intersection of 2 subspaces, like these ones here, C1 and C2. This is the intersection. How can you do that? Von Neumann already studied this in 1933. This was published some years later in 1950. And he proved, this is his book where he published this, that if you have 2 closed and convex, 2 closed subspaces of a Hilbert space, then for any starting point x0, if you start alternately projecting onto each of these sets, this sequence that you construct will converge in norm, not only to a point in the intersection, but to the nearest point in the intersection to the starting point. So let me show you here. If this is the point x0, this means that you project onto the first set. Now you project onto the second set, and then you get x1. You do the same, you get x2, and you continue, and you can see that this is converging to the nearest point of this point x0. Some years later, in 1940, Kakutani also proved the same result. He was unaware of von Neumann's result, proved convergence in norm of the alternating projection for two subspaces. And in addition, this is the paper of Kakutani. I cannot understand anything here, but you can see that he noted in a remark that weak convergence of the alternating projection method also holds when you have M subspaces. So this is written somewhere here. You can see weakly, blah, 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 blah. I don't understand anything else, okay? So it was in 1962 when Halperin proved the result, and he showed that if you have M sets and you want to find a point in the intersection of these M sets, the only thing that you have to do is to start projecting onto each of the sets, and this will converge in norm to the intersection of the starting point. So now we may wonder what happens if the sets are not subspaces. What happens if we apply the same algorithm to the intersection, for example, of this ball and this line? If we do the same, we project, 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 and it looks like this is going to converge to the nearest point in the intersection. Is it always going to be the case? If you do that, for example, with this point Z0, we project, and it converges to this point, and you can clearly see that this is not the nearest point in the intersection. So if you apply to closed and convex sets, it's going to converge to a point in the intersection, but not to the nearest point. And this was proved by Bregman in 1965. And here is a slight difference with the previous result, is that what he proved is that when you have closed and convex sets, the alternating projection method is going to converge weakly. This is why, the reason why I put half an arrow here, to a point in the intersection of all these sets. This picture, by the way, is one of the few that actually is the only picture I've seen of Bregman. You know, Bregman is the one from Bregman distance. And if you look for Bregman on the web, you will not find that picture. It took me like hard work to get this picture. I had to write several collaborators, and finally one of them replied and nicely sent me a picture of Bregman. So let me tell you now about another projection algorithm, which is my favorite one, and also Wallace's favorite one, I might guess. You may have heard of this, of the Douglas-Ratchford algorithm. The way I like to introduce it is using the reflection instead of the projection, because I think it makes it simpler to remember. So what is the reflection? The reflector is simply just you reflect the point x that you have here with respect to the projection. So it can be defined in the same way as 2 times the projection minus the original point. So what is the Douglas-Ratchford algorithm? Instead of doing project, as we did before, what we do is reflect, average. Okay, I will show you. But before doing that, let me tell you a little bit of history about the name. The algorithm is called Douglas-Ratchford because of Jim Douglas and Henry Ratchford, who used it to solve a linear system of equations arising in heat conduction problems. In my honest opinion, it should be called Lyon and Mercier algorithm, because if you dig into that paper, it's really hard to find this algorithm or anything related to that. And the only reason why it's called Douglas-Ratchford is because Lyon and Mercier said that their algorithm was inspired by this method that you can find in that paper, but it's really hard to find it, I have to say. I think Wallace has a paper on that explaining where you can find it. So this is what I told you. The only thing that you have to do now is reflect with respect to one of the sets, reflect with respect to the other, and then take the average with the previous point. So let me show you with a picture. If this is your starting point, this is one of the sets, this is the other set. You reflect with respect to the ball. I reflect with respect to the line. and then I take the average, and this is the point x1. I repeat, reflect, reflect, average. This is x2, x3, x4, x5, x6. And you can see that in this case, in 6 iterations, it has converged to a point in the intersection, which is no longer the nearest point of the starting point, because that would be this point here. What happens if you apply it with 2 subspaces? In this case, it is the nearest point to the starting point. So if you apply the algorithm, you get this spiral, and it converges again to the nearest point of the starting point. So this is the result. Actually, this is not the result by Lyons and Mercier, because what they prove is much more general. But if you apply it to normal cones, so you consider the feasibility problem, then what they prove is that the sequence generated by the Douglas-Rashford algorithm converges weakly to a point such that when you project it onto the first set, is a point in the intersection. So this is a key difference with the alternating projection method, because now the sequence doesn't need to converge to a point in the intersection, but you have to project it. So here you can see an example. This is what happens if you apply to this ball and this half space. This is the sequence. It's going to converge to this point here, but this point is not in the intersection, but you need to project it onto the first set. And this sequence here is the sequence of interest. It's called the shadow sequence for obvious reasons, because it's like the sun is on top and you can see it on the bottom. So because we are working on Hilbert spaces, things are not so easy, and because of that, you cannot deduce from weak convergence of the sequence, weak convergence of the shadow sequence. And this was proved 30 years later by Zweiter, who showed this thing, that the shadow sequence is weakly convergent to the solution that you want to find, so a point in the intersection. So what happens if you have more than 2 sets? Because, okay, a feasibility problem with 2 sets is not that interesting. If you apply alternating projections, we have seen that this works. For example, here you have 3 balls, and you can see that it converges to a point in the intersection. What happens if we do the same with Douglas-Rashford? It doesn't work at all. It's very easy to construct an example. Here we have 3 lines, A, B, and C. And if we start here in this point x0, we reflect with respect to A, reflect with respect to B, and reflect with respect to C. We go back to the starting point. This means that this is a fixed point of the operator, and you cannot find a point in the intersection, which will be this point from this point x0. So this is not going to work. So we cannot apply Douglas-Rashford for more than 2 sets. So is this the end of the story? Can we do something more? Yes, because we can use a mathematical modeling trick and replace the M sets that we had before by a 2-set problem. And in order to do that, the only thing that you have to do is to enlarge your space and to construct 2 sets, C and D, in which the first set is just the product of the Cartesian product of all your sets, and the second one is just what is called the diagonal subspace, in which all the coordinates are the same. So you can see here that I have enlarged the space. All these 2 sets are in a larger space, okay? And, okay, this is nice. You can easily see that these 2 equations are the same, but this will not be useful unless you would be able to compute the projections easily onto these 2 sets, C and D. And this is the case because it's very easy to see that the projection onto this set C is just the Cartesian product of the projections, and the projection onto the diagonal space is simply the centroid of your points. So if you can compute the projection onto the sets, you can compute these 2 projections, and you can apply the algorithm. And this is what I've done here. So if you apply Douglas-Rashford and you apply Pierre-Ras product space reformulation, the algorithm that you get in order to find a point in the intersections of M sets, what you need to do now is different because we need M copies. So we will need M starting points. It's not like before, we have 1 starting point, we have M different starting points. Of course, you can take all of them the same, but there is this freedom that you could take them differently. And the thing that you need to care about is this centroid of all these points, and this is going to converge to a point in the intersection. So let me show you with a picture. So for example, imagine that you want to find a point in the intersection of these 3 balls. We need to enlarge the space. We need 3 sequences of points, x0. So I took them differently. These are the points x0. We compute the centroid. And then what we need to do is to reflect with respect to the centroid, reflect with respect to the first set, and take the average. This would be the update of the first point. We do the same with respect to the second point and the second set. We do the same with respect to the third set. And now we have a new triangle. And we have a new P1, which is the centroid of this triangle. And then if we keep doing the same, P2, P3, P4, you can see that we have already found a point in the intersection of all these sets. Okay, so let's move it forward.
Was that algorithm equivalent to the PR point, or is this a different?
This is Douglas-Rashford simply applied to the PR reformulation. So if you apply it and you write it down, I mean, it's not easy to see just in one slide, but if you take a piece of paper and you write it, it's just 2 lines to write it down, and you get exactly the same expressions. So it's not difficult. So we are in an optimization department, optimization and combinatorics, so I suppose you care about optimization problems, so can we apply this method not just to feasibility, but to a minimization problem? So this is what I'm going to talk about now. So imagine that you have the nicest optimization problem where you want to minimize a function which is convex, is differentiable, and you have a set which is also closed and convex. What can you do? Well, of course, you can use the typical trick in convex analysis. You can use the indicator function, which is equal to 0 if your point belongs to the set and plus infinity if not. And then you can convert this problem into an unconstrained problem. But of course, there is always a price to pay, because before we had a function which was differentiable, and this function is no longer differentiable. But we have 2 different pieces in this objective function, and this is what we will use for our splitting. So what do we know? By Fermat's rule, in this case, a necessary and sufficient condition for optimality is that 0 belongs to the normal cone at the point x plus the gradient of f of x. And what does it mean? So it means that if we want to solve this optimization problem, the only thing that we need to find is a 0 in the sum of these 2 operators, in which the first one is set-valued because it's a cone, and the second one is single-valued. Okay? So this is what we are going to work, is we are going to try to find zeros in the sum of 2 operators. Which is the easiest algorithm to find a point that solves this problem in this which is a solution? Well, it's the projected gradient algorithm, which is basically the same as the gradient algorithm with an extra projection onto the set. So if you further assume that the gradient of your function is Lipschitz, what you can do is simply apply the projected the gradient algorithm. So you take a step into the minus the gradient, and then after that you project it onto your set. So I will do it here. So these are the lever cores of my function. I'm going to try to minimize this function onto this set. And in order to do that, what I need to do is to take the negative gradient. I will move into that direction. I will move this step size, which is bounded by the Lipschitz constant. And then I project, and this will be my point x1. I repeat this x2, and so on. And you can see that this is converging to the point which minimizes the function f inside this set Z. Okay, so we have seen that this is equivalent to finding a 0 in the sum of these 2 operators. So we wonder, can this be generalized? So in order to do that, let's observe the properties of these 2 operators. And what we are going to do is to generalize this and to have the basic properties that will allow us to generate a splitting algorithm for more general functions. So what we need to do is to consider the first operator here. We are going to consider to be maximally monotone. I don't know if you are familiar with monotone operators. If you are not, ask Walla. She's also an expert. If you haven't seen it before, it will be impossible for you to follow my slide, but it's okay because you will see that a particular case of monotone operators is the normal cone. So every time you see one of these operators, you can think about normal cone, and this is a maximally monotone operator. So an operator is monotone if it satisfies this inequality here for all points in the graph, and is further maximally monotone if there is no other monotone operator such that the graph is properly contained in the graph of this other operator. So, and the simplest maximally monotone operator I can think of is if you have an affine function given by mx plus b, is maximally monotone if and only if m plus m transpose is positive semi-definite. More interestingly is the one I told you before. The normal cone is maximally monotone, so we can think of this operator a of x here as the normal cone, okay? And also, more generally, the subdifferential of any convex function is as well maximally monotone. So here we could put the subdifferential of a convex function, and again, we will have a maximally monotone operator. What about the operator B? This is the equation I will try to solve. The operator B, I will assume to be co-coercive. I don't know if you have heard it before. In case you haven't heard of that, it's, these are maximally monotone operators, which are more restrictive because they have to be single-valued, and they must satisfy this inequality here. What is an example of a co-coercive operator? Well, by the Bellon-Haddad theorem, it says that if you have a convex and differentiable function, then the gradient is Lipschitz if and only if the gradient is co-coercive. So what we have seen before in the projected gradient algorithm, that we were assuming that the gradient was Lipschitz, it means that the gradient is co-coercive. So we could put here the gradient. So here we could put the normal cone, and here we could put the gradient, and this would be a generalization of what we have seen before. But, of course, we could do other things, like, for example, putting two normal cones here, and if we put two normal cones there, finding a zero in the sum of these two normal cones is equivalent to finding a point in the intersection of these two sets. Or we could put a subdifferential or other pieces, different pieces. Okay, so if we want to build a splitting algorithm, we need to have something that replaces the projection. And this is the resolvent operator, which the definition is a little bit strange because what you do is you add the identity to your operator and then you take the inverse to that. And this is how the resolvent is defined, okay? And interestingly, if you take the normal cone and you compute the resolvent, you get exactly the projection. So every time in my next slides, every time that you see J, N, J, blah, 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 you can think of projections, okay? So this would be just a projection. If you just care about feasibility problems, this could be projection. But more generally and more interestingly, you can put there the subdifferential of functions. And if you compute the resolvent of the subdifferential of a convex function, lower semi-continuous and convex function, what you get is the proximity operator. And the nice thing is that there are many explicit formulas for computing the resolvent operators. And if you want to see that, I recommend you this website by Patrick Convetz and their collaborators, where you can even find Python code, I don't remember if MATLAB as well, of many proximity operators. So it's really nice. So this was the projected gradient algorithm that I showed you at the beginning. What happens if we now replace the problem with the sum of a co-coercive and maximally monotone operator? We get the forward-backward algorithm, which is actually exactly the same thing. So if instead of wanting to solve this problem, we want to find a zero in the sum of the operators A and B, where A is maximally monotone and B is co-coercive, the only thing that you have to do is to run this algorithm where you take B of xk, this is exactly that we had before, and here, instead of having the projection, we take the resolvent. And this is going to converge weakly to a point which is a zero in the sum of the two operators, which is what we wanted to solve. And why, the reason why it's called forward-backward is quite obvious, is because the operator B is used directly. So this is a forward operation, and the operator A is using the resolvent. So it's used using this formula, we have the inverse. So this is why it's called backwards, because you have to take the inverse. And what is the problem now? This is not the end of the story. This is not the end of my talk. Sorry, I still have more time. The problem is that computing the projection or computing the resolvent in general can be difficult. So what can we do? We can split more. So we can split the problem in more parts, and so that we can compute all these pieces. This is the idea. And the nice thing is that the same thing that I told you before about Pierra product space reformulation, you can do it with maximally monotone operators. So if you want to find a zero in the sum of m maximally monotone operators, what you can do is you can build a two operator sum in which what you want to do is to find a zero in the sum of these two operators. And again, so the first operator is constructed as the Cartesian product of all the operators, and the second set is the normal cone to this diagonal subspace. And this makes sense because luckily, if you compute the resolvent of these two operators, it's very easy as long as you can compute the resolvents of each of the operators, because the first resolvent is just given by this, and the second one is again the centroid of all the points that we have. So the good news is that we can apply a splitting algorithm to these two sets, but again we have a problem, and the problem is, you may have guessed it, every time that we do this trick, we are enlarging the space here. So if your given space H to start with is big, here you are making the Cartesian product of M. So it will be very large, and if this M is large, it will be quite huge, and the algorithm, the resulting algorithm, will be slow. So until 2020, all algorithms use Pierra's reformulation in order to handle or splitting algorithms to handle more than two operators. And in that year, Ernest Rieu, what he showed in this very nice paper is that if you want to deal with three operators and you want to construct the splitting algorithm, you need at least to enlarge the dimension of your space by 2. So this means that you need at least 2 sequences. So you cannot start with 1 point, a starting point, but you need 2 starting points and then to run these 2 sequences. And he showed the first splitting algorithm with 2 sequences that converges to a 0 in the sum of these 2 operators. So 2 years later, Rubén Campoy, my former PhD student, what he showed is that this nice modification of Pierra's product space reformulation, that it looks almost the same if you look at the first part, but the difference is here in red. Instead of having M operators, as we had before, we have M minus 1. And what happened with the operator M? He moved it to this right-hand side, and thanks to that, instead of having a product space of M of size h to the power m, he can prove that you can build a splitting algorithm in a dimension lower, which hopefully will result in a faster algorithm. At least it will require less memory than the other one, because the power will be 1 less. So 1 year later, Yura Malitsky and Matt Tam, they proved that this is the minimum that you can get. So Rubén didn't know about that, but they proved that what Rieu proved for 3 operators is also valid for M operators, which means that if you want to construct a splitting algorithm for M operators, you need to enlarge your space by M minus 1. So this is the minimum, and they also introduced a splitting algorithm for M operators in that paper. And what we did, actually, well, it was not the same year, it was 1 year later, but they were published at the same time. It was to extend their algorithm in order to include as well co-coercive operators. So this is how the algorithm looks like. I know it's quite horrible, but you can see that every time we have a key the resolvent, think of this as projection, for example, we have the resolvent, and here we have the co-coercive operators. And we are taking all these pieces separately. So this means that this is a splitted algorithm. So what about the proofs? How do you prove that this ugly thing converges? The proofs are way much horrible than the algorithm. So for example, this is one of the pages of the paper that we wrote with David. And what you had to do is just to apply Eckart-John, maximal monotonicity, inequalities, 1,000 of inequalities, and then be lucky, then reorder things and be able to finally prove that something is greater or equal than 0 after 5 pages. So there was no general proof, so after all these papers, there came several splitting algorithms, and each of them, they have a different proof. Okay, which was not nice, even though all the proofs were somehow similar, but they were not the same. So you couldn't get one proof from the other. So this is what I'm going to talk about now, is how all these proofs can be summarized and how can all these generalize and using graphs, okay? So this is a Malitsky-Tamm algorithm, which is the same as we had before, the one I showed you before, for just 3 sets and without co-coercive operators, okay? So if you look at this algorithm, you can see that there are 2 types of variables. The ones I just put in blue, this is just the result of computing the resolvent. So you compute the resolvent, resolvent, resolvent. So these are called resolvent variables. And what Christian Vredis, Enis Chen and Emmanuel Naldi realized is that you can model these variables with a graph and a subgraph. You have other variables that are, we call them governing variables, and what you can do is to construct a graph in which each of the nodes represent each of the operators. So for example, here we have 3 operators, so we have 3 nodes. So the first graph, what it tells you is what you do after you compute each of the resolvent variables. So for example, the first one, we compute the x1. What do we do with x1? We send it to the second node. So this means that x1 is going to appear here. And the first one, you send it to x3, so it means that x1 is going to appear here. Okay, so we can see how x2, for example, you compute it, and then you send it to x3, so this is why you have x2 here. So what about the subgraph? This is a subgraph of the graph here on the left. And in general, it's not so easy to explain, but in the case, the role of this graph, in the case where you have a tree, if your subgraph is a tree, what you can do is you can associate each of these variables, of the governing variables, to one edge of the tree. And in such a case, what you can do, and how this is modeled in this algorithm, is that if you have a variable that is going out of one of the nodes, you have a plus sign in the resolvent. So you can see that W1 is coming out from the first node. You have a plus W1 is entering into the second node. This is the reason why we have a minus in here. And similarly with W2 is coming out from the second node, so we have a plus here, and it's entering into the third one, so we have a minus here. Okay, this is nice. You can represent the algorithm with a graph and subgraph, but this is not so important. The important part is that if you draw a graph and a subgraph for each of these, you get a splitting algorithm that converges. So this is the really nice thing, is that you don't need to care about all these proofs as long as you have a connected graph and subgraph where all the nodes go forward, then you get a splitting algorithm. So this is what we call algorithmic graph. So the requirements are very simple. So you have a node for each of the operators. You have the edges represented by this E. And the only requirement on the edges is that if yj is an edge, then y has to be smaller than j. And what is the reason for this requirement? Is because if you haven't computed a variable, you cannot use it in another operator. So this is the only requirement. And you need your graph to be connected, because otherwise you will be computing some variable and then not using that variable with respect to the rest of the variables. Okay? So very easy. So these are a few examples of algorithmic graphs. All the nodes have to go forward, but there are, of course, many, many more algorithms that you can, graphs that you can consider. And we are going to need the Laplacian matrix, but here probably I don't need to explain what is the Laplacian matrix. I suppose most all of you know, because where we are. Just in case someone doesn't know, the Laplacian matrix, what you have in the diagonal is the degrees of each of the nodes, and it has a -1 if one node is connected to the other one. So for example, 1 and 2 are connected. So this is the reason why you will have a -1 here. 1 and 3 is connected, -1. And 2 and 3 are not connected, so we have a 0. Okay, but we not only need the Laplacian, but we need a decomposition of the Laplacian, an onto decomposition of the Laplacian. And this means that we need a matrix set such that when you multiply Z by Z transpose, you get the Laplacian. And you can always do that thanks to the properties of the Laplacian matrix, which is positive semi-definite. It has a 0 eigenvalue, and the other eigenvalues are positive. And therefore, what you can do always is to take an orthonormal basis of the Laplacian, and then construct the matrix in this way. Of course, this is not so easy in general because you would have to find these eigenvalues, etc., etc. So it's not so nice. The nice thing is that when you have a tree, and this is the reason why it was easier for me to explain the case of the tree, you can always take the incidence matrix as this onto decomposition. And this will give you just the matrix set that it will be needed in our algorithm. So this is the setting of Bredis, Chen, and Naldi, and what we did was to consider to add also cocoercive operators, and in order to do that, to model the cocoercive operators, we need another subgraph of the original graph. So we have a triple of graphs. We have a graph and 2 subgraphs. And for this graph, what we ask is that each of the nodes have a unique predecessor. So you cannot have, for example, in this graph, we couldn't consider these graphs because, for example, the n node has 2 predecessors, so there are 2 arrows going into there, and we cannot use that one either because there are many that are not satisfying that. So this is the algorithm that we propose. So given a set of n-1 starting points and some parameters here, if you have a triple of graphs G, G prime, and G prime prime, and you have an onto decomposition of the Laplacian, this is the algorithm that, the splitting algorithm that you get. And we can prove that this converges to a solution of the the inclusion problem of 0 belongs to the sum of the operators. So how do the graph appear here? The first graph, G, appears here in the degrees that you have here, and also in the edges that you have here. So the number of variables that you sum in here. The second graph, G prime, appears in the algorithm through the matrix set, which is the onto decomposition of the Laplacian. And the third one, it appears here. It tells you which cocoercive operator applies to each of the variables here. And this is the theorem of convergence. And what we prove is that for any starting point, then a governing sequence is converging, weakly converging to a fixed point, such that the shadow sequence converges to the resolvent operator of this fixed point. So, and this shadow sequence, all these shadow sequences give you a solution to the inclusion problem. So, just with these 3 graphs, you can prove convergence of many algorithms. And for example, let me show you quickly, you recall this paper I show you with all these inequalities. The only thing that we need to do is to put a graph, so the ring graph. If we have the ring graph, the degrees are equal to 2, so the only thing that we have to do is to replace these degrees by 2. We have this, and now we take the sequential graph as the subgraph. It's a tree, so we can take the incidence matrix as the onto the composition. We replace that into the algorithm, and then we make the replacement to make it look similar, but we already have exactly the same algorithm that we had before. And just in this slide, with the graph and the subgraph, you have the proof of convergence of this algorithm. And not only that, you have many, many more algorithms. For example, this is another one from another paper. And you can prove just with this graph and this graph that this is convergent, and you don't need all the analysis. Just doing that, and then you have the algorithm. And then we thought, okay, what happens if you take the complete graph? If you add all the connections, is it going to be better? Is it going to be faster? Is it going to converge? Well, here the situation is a little bit more tricky because if you want to construct an algorithm, a splitting algorithm, now if you take the graph and the subgraph as the complete graph, it's no longer a tree. So you need to find an onto decomposition of this graph. We managed to do that in general, and we ended up with this algorithm over here. So what can we say about the limit points? I think I'm probably going, how am I about the time?
We've got 20 minutes.
Ah, okay, so I can talk about the limit points. I've been doing well with the times. So what can we say about the limit points? So this is the Douglas-Rutherford algorithm, which I tell you before that it converges to the nearest point of the starting point. So when we have subspaces, this is what we analyzed in our most recent paper, is the situation where you don't have co-coercive operators, okay? So where do these algorithms converge? So what we realized is that what you need to pay attention is into something that we call the degree balance of the graph. What is the degree balance? It's a fancy name just to say how many edges are going out and how many edges are going in. And you subtract the number of edges going out minus the number of edges going in. Okay? So then this is the degree balance. You remember the matrix Z, that was the onto decomposition. So you take the Moore-Penrose inverse of that matrix Z. This gives you this vector alpha. And then what happens? Well, if you have that G and G prime are equal and are a tree, then it's not very difficult to prove that this constant is always equal to 1. And what we prove is that, in general, this algorithm is going, when you apply it to normal cons of subspaces, that means that you are doing projections onto these subspaces, is going to converge strongly to this point. And the point, what you have here inside, is just this vector alpha. Okay, so this gives you just the point where your algorithm is going to converge, which in general is not easy to compute. And what happens, for example, with the Douglas-Rutherford? In the Douglas-Rutherford case, we have, it's very simple because we only have 2 nodes. And then it's a tree, so alpha is equal to 1. So alpha here is equal to 1. So this is telling you that it's going to converge to the nearest point in the intersection. And what happens more generally if we use the complete algorithm? This would have been quite crazy to analyze if we didn't do it in this way, because the algorithm converges to a very strange point. So the point that it converges, we can prove it just using the previous theorem, is that it's going to converge to this weird point here. It's not just the nearest point of the starting point or a combination of the starting points. You have this weird sum over here where this constant Tj are equal to these constants over G, here on the right. So for example, here, I don't know if you can see it, there are 3 subspaces over here. I will apply the algorithm with 2 starting points. Remember, if we have 3 sets, we need 2 starting points. If I do that and apply our result, this tells me that the governing sequence is going to converge to these 2 red points, and the shadow sequence, the one that we project, is going to converge to the nearest point of this point here. This point here is this point I computed here in purple, the projection onto the intersection. And you can see this is what happens. If you run the sequence, this is the first sequence, this is the shadow sequence, so you project onto this subspace, and you can see that it's converging to this point here, exactly. Okay, you can see it here, I can turn it a little bit, and you can see the intersection. Okay, so just to finish, I'm sure that you're already a little bit like, your mind is like that, probably. Let's move to something nicer, which is my open question. So the open question is related to the use of Douglas-Rutherford in non-convex setting. So there is something that I find very interesting, is that Douglas-Rutherford algorithm, for example, when you use it for convex sets, it's guaranteed to converge. But in some situations, in very non-convex sets, the algorithm still converges and can find solutions to inclusion problem. And one of these cases is with graph colorings, and in particular with Sudokus. You know that Sudokus can be modeled as graph colorings. You can assign to each of the numbers one color, and you can model the Sudoku by a graph. You have it here on the right. And in order to solve a Sudoku, the only thing that you have to do is to color this graph so that there are no nodes connected which share the same color. So if you look at this graph, no wonder why it's so difficult to solve some of the Sudokus, because you have to color this mess with different colors so that the edges don't share, I mean the nodes that have an edge don't share the same color. So the very interesting thing that we saw in this paper, in the first one, is that you could model Sudokus as a feasibility problem, and then you can apply Douglas-Rashford and solve almost every Sudoku. And this was not so annoying because it failed in some situations. So I think we tested, I don't know, not so many Sudokus, because that was in almost 10 years ago. We tested like around 50 Sudokus, and I think we got like 95% of the cases of the starting point, it converged to a solution, and it gave you a solution to the Sudoku. But the most annoying thing is this paper from 6 years ago. And this formulation, I find it interesting. Well, this is the solution of the Sudoku. Spoiler alert, sorry. This formulation is quite nice because it involves semi-definite programming and a completion problem. So you can model the graph coloring problem as a matrix completion with two sets, in which the first set is just a matrix with two possible entries, either 1 or -1 divided by the number of colors -1. And the second set, well, these are the entries that have been pre-assigned with some colors. And the second set is the set of symmetric positive semi-definite matrix with rank less or equal than n-1. And if you want to color, for example, this simple graph that we have here, the only thing that you have to do is to fill this matrix here on the right, so that the matrix satisfies these two is a point in the intersection of these two sets. So for example, this would be a possible solution of this graph coloring problem. And why is this a solution? Because here, if we have a 1, this means that these two nodes share the same color. So for example, in here, what we are doing is node 1 and node 4, they share the color. Node 2 and node 5, they share the same color, and node 3 has a different color. And the other ones have different colors. When you have a different color, you have -1 divided by n-1. So you can run Douglas-Rashford onto this, because the only thing that you need to do to run Douglas-Rashford is to project, to be able to compute the projection. And it's very easy to compute the projection onto this first set. It's just to find the nearest point in each of the entries of the matrix. And into this one, it's also very easy, because you have only to find the nearest positive semi-definite matrix with a given rank. So you only have to compute the eigenvalues and take those that are smaller, larger, and no, smaller. Yeah, take out of those that are negative, and so on. Okay. And the annoying thing is, for example, this graph. What I did this year as an undergrad project was to retake this and to test a Kaggle database of 9 million of Sudokus. And she tested all these Sudokus for, in this case was for a random starting point. And in all the cases, there are not 9 million here, because I had to leave, I had to come here, and I had to stop the computation. But in 8,000,000, blah, 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 or in all these cases, in every single instance, it found a solution of the Sudoku. And it found a solution in 0.5 seconds on average. So you can see here, this is the 95 bottom of all the distribution times, and you can see how most of the Sudokus, they were solved like in 0.1 seconds, so very, very fast. And I didn't do any fancy programming. Just to finish, some advertisement. I've been acting as a editor-in-chief, co-editor-in-chief of the journal Top, Transactions of Operation Research. And of course, I invite you to submit your work there, and I'll be very pleased if I see your names when I receive the paper. So this is all. These are the main references. I strongly recommend the book by Walla and Hines, because if you want to get a very nice introduction onto these splitting algorithms, I think it's the best place to go. So thank you for your attention.